In this lesson, you will learn how to simplify radicals. We begin by defining a radical. What is a radical? And what are the parts of a radical? Well, what you're looking at right now is an example of a radical. When we have a radical, this is an expression that has a square root, a cube root, or some other kind of roots. You'll recognize it because first you'll see a number here. If there is no number, that's called the index. If there is no index, then it's an implied 2. You'll also see something called the radicand. The radicand is the number underneath the radical symbol. And the radical is that number. It's what we refer to as, in this case, the cube root of 27. What does it mean to simplify radicals? Well, to simplify radicals, it means to reduce the radical to its lowest terms, kind of like you would do with a fraction. If you had the fraction 3/6, we would reduce that to be 1/2. Radicals can also be reduced to lowest terms. We're going to start looking at how to simplify different radicals. And we're going to do this by using prime factorization. Although this is not the only method, it is going to be the method that I will show you in this module. Number 1, we have the square root of 147. So we're going to begin by looking at the prime factorization of 147. What that means is we want to know what numbers multiply together to give me 147. Well, if you cover it up and you kind of look at the number 14 and you look at the number 7, you probably recognize that that's divisible by 7. So we can say 7 times 21 will actually give me 147. 7 is prime, so we're going to circle that. The number 21 is not. However, if I do 7 times 3, both of those are prime. So now we're down to just prime numbers here. So now we can rewrite this radical of 147, and I'm going to put these numbers in order from least to greatest. It helps keep me organized. So 3 times 7 times 7. And if I multiplied all that back out, I would get the number 147. What I'm looking for is what I'm calling twins, because this is a square root. It's an implied 2. We're looking for groups of 2. And I see a group of 2 7s. Now, when you pull it out, you only get to pull out one of those numbers. Because think about it. 7 times 7 is 49. And if we took the square root of 49, that's equal to the number 7. So when you take out a twin, you only get to take out 1. So that's going to make this 7 square root of 3, because we have now used up the set of twins. So one of the 7's comes out, we cancel it out, and what we're left with is 7 square root of 3. In our next example, we have the square root of 180. So we're going to take the square root of 180, and again, we're going to go for its prime factorization. Anytime a number ends in 0, it means that that number is divisible by 5. So I'm going to divide a 5 out of this. 5 times 36 gives me 180. Now 5 is prime, so I can circle that. 36 can be broken down into 6 times 6, which, by the way, I point out is a set of twins, and we could actually stop right there. But for the purposes of this module and going all the way to the prime factorization, we're going to keep going. 6 is made of 2 times 3, so both of those are prime, and we can circle both of those. Same with this 6. It's made up of 2 times 3. Now I'm down to prime numbers. So I'm going to go ahead and put the big square root symbol, the radical symbol, and I'm going to put these numbers in numerical order. So I've got 2 times 2 times 3 times 3 times 5. Now I'm looking for sets of 2. When I look for a set of 2, I'm going to circle the twin, and I see a second twin in here. How many do I get to keep when I pull one out? Only one of them. So I'm going to pull out a 2, and I'm going to pull out a 3. So that means that I have a 2 on the outside times a 3 on the outside. That means that cancels and that cancels. And now I still have the square root of 5 left. It didn't have a buddy, so it's staying inside. Now all I need to do to finish this is 2 times 3, which would be 6 square root of 5. And that will be my final answer. On this next example, what you see is x to the 7th inside. That's our radicand. So we have the square root of x to the 7th. What does that mean? Well, we can actually go straight to the prime factorization. It means I have x times x times x times x times x times x times x. I have 7 x's here that are being multiplied times each other. And I'm still looking for groups of 2. So here's a group of 2, here's a group of 2, and here's a group of 2. How many x's am I able to pull out? 3 of them. That means that's going to be x cubed, but I still have 1 x that was left inside, so it's going to remain the radicand, and that would be my final answer. Now, there is a shortcut whenever you're dealing with variables. Basically here, since this is the square root, it's got a root of 2 or an index of 2, we'd want to know how many times could 2 go into that 7 evenly. And 2 can go into that 7 evenly 3 times, like my x cubed. And there would have been 1 left over, like my radicand, just the x. So you can use that shortcut, especially when they ask you to find something like the square root of x to the 2,000th. That would be miserable to write out 2,000 x's. So you just say, okay, well, I should take that number 2,000 and divide it by 2, and that would help you simplify much more quickly. In this next example here, I have a set of variables. So I have the square root of x to the 4th times y times z to the 5th. Now, I'm going to show you both ways, the quick way and the longer way. I'm going to start with the longer way. Here I've got 4 x's, 1 y, and then 5 z's. And remember, we're looking for sets of 2. So there's a set of 2 x's, there's a set of 2 x's, there's a set of 2 z's, there's a set of 2 z's. You only get to take out 1 of each of them. So how many x's do I have in all that I'm taking out? I have 2 groups, so that's x squared. So there goes the x's. How many z's? I have 2 groups, so that's z squared, so there go my z's. Inside still, as my radicand, I have a y and a z, so this would be my final answer. But let's back up. Let's not write out the prime factorization of this. Rather, let's do this problem, x to the 4th, y, z to the 5th, where we have the radical around them, and let's think about it in terms of the fact that the index is 2. If you don't see the number there, it's 2. So how many times can 2 go into the exponent of 4 evenly? Twice. That means I can take out 2 x's. I'm done with my x. Then how many times can it go into the y evenly? None. So that y's got to stay inside. How many times can 2 go into 5 evenly? 2 times. So that would be z to the 2nd power. But did I use up all the z's? No. 2 times 2 is 4, which means I still had 1 z left. So same answer, just a little bit different approach to it. In our next example, we have the square root of 40 x to the 11th. Here with our 40, let's go ahead and do the prime factorization. 40 is 5 times 8. Now 5 is prime, so we can circle that. 8 could be 2 times 4. 2 is prime, so we can circle the 2. 4 can be broken down into 2 times 2, so we'll circle both of those now. So now we're ready to write this radical. Here I have 2 times 2 times 2 times 5 and times x to the 11th. We're going to do our shortcut way on that variable. I'm looking for sets of 2's, so I'm going to circle this set of 2's, and I can pull out only 1. That's done. Now, think about how many x's can we pull out? How many times does 2 go into 11 evenly? It can go into 11 5 times evenly. So now, let's take our radical, and what's left? We have 2 times 5, which is 10. And before we took out, how many times did 2 go into it evenly? We said 5, but there's still 1 x left. So that would be my final answer here. In our final problem, this one is slightly different, and it's because if you'll notice, our index has actually changed. We're looking at the cube root of 108. Now, let's go ahead and do our prime factorization and see how this problem changes a little bit. 108 is one of our multiples of 12, so that would be 12 times 9. Neither one of those are prime, so we got to keep going. 12 can be 4 times 3. 3 is prime. And 4 can be broken down into 2 times 2. Those are both prime. Now, in terms of 9, 9 can be broken down in 3 times 3. So let's go ahead and rewrite this. We have the cube root of, now let's put it in numerical order, 2 times 2 times 3 times 3 times 3. Now, this index number tells me what groups I'm looking for. And when the number changes to 3, an index of 3, I'm looking for groups of 3. So I only have one set of 3 numbers that are the same, and they happen to be 3s. So when I pull them out, the rule still holds. I only get to pull out one of them. So only one of those 3s is going to come outside. So I've got 3. Don't forget your cube root, and what's still inside? Well, those 3s are gone. 2 times 2 is left, so it's 3 times the cube root of 4. And now I have simplified my answer. In this lesson, you learned several valuable skills about how to simplify radicals. You learned what the parts of the radical are. You learned how to simplify a radical with a constant as a radicand. You learned how to simplify a radical when there was a variable as a radicand. And you also learned how to simplify a radical when we have both constants, numbers, and variables underneath that radical symbol, and they're acting as the radicand. I hope you found this lesson useful, and now it's your turn. Now it's your turn to actually try the problems on the next set in the module.